Okay, we'll go back here. Since apparently there's audio issues and probably Zoom issues here, we'll go over this as well. Okay, so again, sorry, matter properties. Okay, matter is the physical material. Okay, it has mass and occupies space. All right, so again, we're talking about solids, liquids, and gases here. Fourth one is plasma, but we don't really talk about it. Okay, then matter is composed up of atoms. It's the smallest unit that we have. Okay, so it says it's the smallest part of any element that is still an element. And then a molecule is two or more of those joining together to act as a unit. All right. So again, for example, oxygen atom, hydrogen atom, both of those are individual atoms. When we put them together and add an extra hydrogen atom, we come up with water, which is also known as H2O, right? Okay, another example, carbon monoxide, that's just CO. Okay, so one carbon atom, one oxygen atom. All right, it has this pollutant. Okay, carbon monoxide itself is a molecule. All right, but of course it is made up of a carbon atom and an oxygen atom. All right. 4 atoms and molecules. Okay, basically, if we're trying to understand the substances around us, okay, then we need to understand atoms and molecules that compose of them. All right, and essentially, this is the goal of chemistry. Okay, if we can explain and understand what's happening at a molecular or atomic level, we can pretty much explain the rest of the universe. Or at least that's what we try to do with chemistry. Okay, so essentially the big topic is that chemistry is the science that seeks to understand the behavior of matter by studying the behavior of atoms and molecules. Right, so we're trying to understand the physical world around us by understanding the things that make it up. Atoms, molecules, elements, that stuff. Okay. So for states of matter, like I said, we have solids, liquids, and gases. Okay, we're pretty familiar with all of those. So sugar versus water versus the vapor coming off of coffee. All right. If we look at a more molecular level or atomic level here, okay, we are talking about things in terms of particles. All right. And of course, when I draw a particle, I'm going to draw it as, a circle, a square, a triangle, whatever you saw on those worksheets. All right. So again, a gas here. Okay, they call it total disorder. Okay, basically, it's going to occupy that space. A gas has no definite volume and no definite shape. All right, again, think about it. The gas in this room, okay, my doors are open. It is where it is. It's contained in this volume. But as soon as I open the windows, that gas is going to leave. It's not stuck here. All right, so again, gas has really no definite shape or volume. Versus a liquid. Okay, a liquid has a definite volume, right? I can't add more coffee to my cup all of a sudden, okay? But it takes on the shape of the container. If I pour it in here, if I pour it on the floor, it's going to take up that container. And then finally, obviously, we have solids, okay? So those don't really move a whole ton. If we take, again, just some definitions for you here, a little bit deeper, solids have both definite shape and volume. Okay, so that was one of the questions on your worksheet, was define these in terms of shape and volume. So again, solids have a definite shape, definite volume. Okay, technically, if we were to look at this table or look at your iPads, technically the molecules in that solid material are vibrating and moving very, very, very slowly. Okay, believe it or not, right? And I don't know if anyone's ever done this or seen this. Maybe Mr. Tooley can validate it for me. But if you've ever been to like a really, really old building or church or warehouse, okay, if you've ever seen really old glass windows, you're going to notice that at the bottom of the glass window, it seems like the glass gets thicker, right? Or it's thinner at top and thicker at the bottom. The reason that is because the molecules of glass are actually vibrating really, really slowly. And over time, they fall down and start to settle because of gravity. So if you actually look at a window, you should see a thickness difference. It's kind of cool. Right, Julie? You ever been to one? No? Cool. Have his headphones in. All right, so then there's different types of solids depending on how those particles are arranged. So there's 2 types, crystalline and amorphous, or those are the 2 that we're going to talk about. All right, crystalline is probably pretty easy. It has the word crystal in it. All right, and if you think of a crystal, basically it means it's ordered. All right, versus amorphous, which again is another ACT word that you could be familiar with. amorphous means having no definite shape, potentially, right? So if you're an amorphous solid, I think of like silly putty. Okay, so examples of crystalline solids: diamonds, ice, salt. Okay, things that are not crystalline, more amorphous would be, again, charcoal, glass, and plastic. All right, so again, looking at this from a particle level or atomic level, crystalline is super ordered, everything looks neat, nice, and beautiful. Versus amorphous, where, again, it's still compact, right, but it's not as ordered. Okay, ooh, somehow I jumped really far back. Apologies, boys. Okay, then looking at liquids, okay, they have a distinct volume, obviously, and they have no specific shape, because again, I can take my coffee, pour it in a different container, and it's going to take on that shape. All right, and this one, of course, the molecules are more free, they're less constrained, so it's more obvious to see them being fluidic. All right, however, I cannot continue to press down on my coffee. Okay, I'm going to get some resistance, more or less. Right? And again, just a couple examples of different ones are water, alcohols, or vegetable oils, okay? And that's talking about this thing called polarity. And again, just bringing up more words that hopefully are gonna remind you of something you've already learned, okay? But we'll talk about these, that they have different properties depending on the atoms that make them up. All right, finally, gases here. They have no fixed shape or volume. Okay, they're going to conform to whatever container they are in, all right? But the thing that's different about this from a gas to a liquid is this, the word compressible, which means we can push it down, all right? So again, a solid, all right, if you've ever seen, I definitely know it's a Snapchat thing, right? They have, I think, like called the crusher or something. It comes down and it crushes materials, okay? Right, so with a solid, at some point, that solid's going to snap, all right? But when you do this with a gas, okay, there's actually very, very little resistance until it gets really, really small, because you can push this gas, you can compress it down, all right? Now, if we transition between the states, okay, we talked about it, there's basically 6 main ones that we're gonna focus on. Again, eliminating plasma. All right, so when I go from a solid to a liquid, I'm obviously melting. And if I go from a liquid to a gas, I'm vaporizing. We're going through vaporization. All right, if I go the other direction, gas to a liquid, that's condensation. All right, and liquid to solid is freezing. Okay, and then the two that are maybe not as common or familiar. If I go straight from a gas to a solid, it is called deposition. All right, it's called deposition. And if I go from a solid to a gas, it's this word sublimation, all right? A really common example of solid to gas is dry ice, okay? So solid piece of ice, dry ice, okay, and it goes to a gas. All right, and the thing that you need to note here is that it takes a lot of energy to go from a solid to a gas, all right? Or solid to a liquid, it takes a lot of energy. Liquid to gas, it takes a lot of energy. But when I go in the other direction, from a gas to a liquid or a liquid to a solid, I'm actually losing energy, okay? Again, think about it. The particles stop moving, all right? They're not moving as much. Again, hopefully in physics, you talked a lot about kinetic energy, potential energy. So again, by slowing down, you're losing that energy. All right, last little bit here. Matter can be classified as either pure substances or mixtures, okay? So again, pure substances are unique materials. They have specific chemical and physical properties, and they're made up of one type of atom or molecule. All right, versus mixtures, which are combinations, but they retain the properties of the individual components that make them up, which means that they can be separated by physical means. All right, and to give you a high level, pure substances versus mixtures. All right. And then quickly, here's something I didn't ask you about, but you have to kind of be slightly familiar with it, is intensive versus extensive. All right, so again, intensive is independent of the amount of substance present. So I and I, intensive is independent. All right, usually it's used to identify substances. So temperature, melting point, color, right? Again, intensive properties. It doesn't matter how much you have, it's not going to change. Versus extensive properties, okay? It changes as the amount of matter changes. So mass, volume, weight, those kinds of things. All right. Then here quickly, because I know you guys did a really good job with your presentations, elements versus compounds. Okay, obviously we have two major compounds, ionic and molecular, also known as covalent. All right. Mixtures, we have two, heterogeneous and homogeneous. Okay. And again, the difference between those two is if it's observable boundaries between the components. If you could look at it and tell me that there's multiple things in there, then it's heterogeneous. Versus if you look at it and you can't tell me the difference, then it's homogeneous. All right. So looking at this here, okay, obviously in the red one, we have, oh, perfect. All right, in the red one, we have our pure substance, right? Our element by itself, okay? Then our compound, and then we have our two mixtures. Okay? So again, atoms, molecules of a single element, molecules of a compound, and mixtures of elements and compounds. Okay? So again, the classification of matter, you ask yourself, is it uniform? If no, it's a heterogeneous mixture. If yes, it's homogeneous. All right? Then, does it have a variable composition? Meaning, is it made up of one or more things? Or sorry, more than one thing? If it's yes, it's going to be a homogeneous mixture. No, it's a pure substance. Element, compound, heterogeneous, homogeneous. All right, and this is another one. I don't particularly like this one. Okay, I think everybody probably found the other one where it just said matter, split it into pure substance versus mixtures, split that into homogeneous and heterogeneous, right? So again, I don't typically like this one that I'm showing you. So whatever one you hopefully found instead will be a little bit easier for everybody. Okay, so if we were to walk through these examples here, helium's obviously an element. Lithium carbonate, okay, is a compound. Lithium something, carbon is something. So it's two atoms put together, makes it a compound. Apple pie, heterogeneous mixture. You can tell me what part is the apple, what part is the filling, what's the crust, right? So it's not consistent through, okay? Versus tea with sugar. If you mix it up really well, you can't tell me the difference, so it's homogeneous, okay? Wet sand is actually a heterogeneous mixture, okay? Because you've got sand and you've got water. Versus salad dressing, okay, is also a heterogeneous mixture. So I'm thinking of like vinegar and oil or ranch dressing or blue cheese, right? You could pull out individual parts. Calcium nitrate is obviously a compound. And then Raisin Bran cereal is also a heterogeneous mixture. Or also could have said like Fruit Loops, something along those lines. Something where there's multiple parts or multiple colors. Okay. Then the last thing here that I asked you on your thing was different types of separation techniques, okay? So if you have something that is a heterogeneous mixture, you can use filtration or centrifuge, okay, or centrifugation, all right? If it's a homogeneous mixture, you've got to do a little bit more work here, and we can use this thing distillation or chromatography, all right? Now, show of, head nods. Are we at least familiar with these words? Okay, have we done filtration, right, in the STEM project? I'm assuming we haven't done centrifugation. All right. Distillation, have we done that? Maybe. Well, I'll explain in a second. How about chromatography? All right. Awesome. Well, so the first one here with centrifugation, basically one of the things you can do is you can get a mixture to separate, okay? You can get a mixture to separate. So what would happen is you can clearly see that there's two layers here. So basically with centrifugation, you spin something incredibly fast and have it settle to the bottom. All right, so I don't know, you and some buddies go to the lake, you go diving, you pull some stuff out, you've got your things, your sand, your water. If you spin it around really, really, really fast, all the heavy particles will fall to the bottom, okay? So you'll be able to take out the water on top. All right, really crude example for you. All right, Versus filtration, this is the one that everybody nodded their head that they've done before. So filtration's pretty simple. Obviously, we'll have to go back through the process of doing that, but that's an experiment for a later time. Okay? Now, if it's homogeneous, okay, we can separate salt from water. And again, you guys did that during your STEM project. You just might not have called it the same thing. All right? So this is technically what distillation is. Or what you guys did was you evaporated out the water probably, right? With your STEM projects, okay? So if you evaporate out water, that is just straight up evaporation. But if you were to put some kind of attachment, like you can see here, if you were to put some type of attachment, when you evaporated the water, you could actually collect it down and count out how much water you had without actually just boiling it off. All right? Now, that is it. Okay, that is it for the presentation here. Okay? Perfect. All right, so that is it in terms of your presentation. Now, I wanted to make sure that everybody at least got the same kind of background information. All right. I know that was a lot, but my hope was that you got most of that and there was maybe one or two new things in there. Okay. Before I keep rolling here, boys, virtual or in person, does anyone have any immediate questions? Okay. All right. Okay, so assuming we have, again, no questions since nobody's, volunteering, which is totally fine, okay? My hope is that we can now go through the worksheet together here. So again, make sure we've all got the same answers. And if we all have the same answers, then we don't have to spend a few days going over handwritten notes. We can all assume that we know what's going on here with matter. All right. So, like I said, I'm going to share my screen. We'll kind of work through these answers here together, as many as we can get through. And then if you've already turned it in, great. Don't turn it in again. Don't unsubmit it. Don't resubmit it, okay? You're more than welcome to fix your answers if you got something wrong. Obviously, these are part of your notes, okay? If you haven't turned it in, this is a saving grace for you. I'm giving you an opportunity to write your answers with the class and to still be able to turn it in for points. Obviously, you're gonna get 10% off for the STL policy, but hey, 10% is a lot better than a 0. Or 90% is better than a 0. Now my Wi-Fi hates me, so it's still trying to connect here. All right, apologies, boys. Awesome, okay, so now we're rolling. All right, so again, what is a mixture? Okay, what is a mixture? Let's go with AJ. What do you have written down for what is a mixture? Perfect, that's a great explanation. State of matter that has more than one substance and can be separated. Okay, sure, that's a great one. And again, he used words that actually make sense to most people, right? Again, don't just pull a definition and use a high-level word if you can't explain it. All right, perfect. So then, Dan Hughes, what's the difference between a mixture and a pure substance?
I don't have my worksheet done.
That's okay.
But
how about if a pure substance is one type of atom or molecule? What's a mixture?
Multiple, like many.
Right, perfect. Multiple substances. Right, at the very, very crudest answer, okay? A pure substance is one type of atom or molecule. All right. And then with a mixture, it's multiple substances or multiple atoms, molecules, some combination thereof. Okay. So then the difference between a mixture and a compound. Okay. Mixture between, the difference between a mixture and a compound. Brian, what'd you say? I love that. I think that's a great example. Okay, he said chemical combination versus physical combination. Right, that's perfect. Okay, because a compound, you would have to do some serious work in order to split that apart, right? So take our water example, H2O. That's gonna cause a lot of issues trying to separate that hydrogen from that oxygen. Versus if I have water and sugar, okay, I can more easily separate sugar from the water. Okay, more easily separate those. Now, hopefully we know this. To separate a solid from a liquid, we should use filtration. I can't spell. T-R-A-T-I-O-N. Filtration. Right? To separate a solid from a liquid, we could just use filtration. To separate a dissolved solid from a solution. What'd you say? Okay. Hey, hit it. Chromatography. We could also use distillation. Either of those two methods. Right? And yes, technically, if you would have said that evaporation, that technically counts as well. All right? But evaporation is a sophomore level chemistry answer. All right? So an AP level chemistry answer would be chromatography or distillation. All right? Awesome. So then looking here, Jimmy G, virtual Jimmy. Okay, walk me through these three pictures. All right, I need to know if it represents an atom or a molecule. So
all right, so the first one's a molecule, and then the second one's an atom, and then the third one's a molecule.
Perfect. Easy, hopefully. Okay. And clearly we know this because in this picture, we have 2 atoms together. In this picture, we have 3 atoms together. All right. On tests, quizzes, anything I give you, you are more than welcome to draw a picture at all points, right? You are more than welcome to draw a picture instead of writing things out, as long as your picture is clearly able to be followed. All right. Now, if we look at this one here, Hootie. All right. Pure substances and mixtures, which is which? Ben Hootie, are you here?
Yeah.
Cool. So of these 3 pictures, which one's my pure substance and which one's my mixtures?
The first 2 are pure substances.
Thank you. Okay. And this is a really good image for what Brian was talking about earlier, right? So I used the water and the sugar water example, okay? So this could very easily be your water, and then this could be your sugar and your water molecule, right? So this is a really good visual representation. All right, Colin, in your best way possible, explain to me what makes an atom different from a molecule.
Well, an atom is like the smallest thing that you could possibly get, and a molecule is made up of atoms and can be made into a compound.
There you go, right? Made up of 2 or more atoms. Right? And then he even said can be made into a compound. Right? So again, very simple. Atom's the smallest unit, molecules made up of 2 or more atoms. Done. Okay? Mike, explain to me what makes a pure substance different from a molecule? Compounds found in nature, right? And you said a mixture is what can be physically separated? Physically combined and can be separated. Perfect. And I'm going to add a word in there. Easily separated. Okay, easily separated. Because technically, pure substances, we can rip those apart. It's going to take a massive amount of energy for most of them, but we can technically do it. All right? Perfect. Okay, now looking at these 4 images here. Let's go with Burnell. Charlie. Okay, label these as elements or compounds for me, Charlie.
I look at my sheet. I kind of forgot.
Absolutely, look at your sheet.
So the first one I put element, the second one I put compound, the third one I put element, and the fourth one I put compound.
Okay. Can you explain to me why? Very simply, look at the pictures. What's the difference between, let's go with this first picture and the second picture. Why is one an element and one's a compound? How'd you know?
Well, I thought it was an element because there's only one shape, and in the compound there's 2 different shapes.
Riley, how's that make you feel? Say that again. So you said same 2 elements. Perfect. Okay, so Riley, based on your definition / explanation, do you agree with Charlie's labels? Perfect. Good. All right. So both of them are correct at a very observable, easy level here, right? Charlie immediately noticed, well, obviously, the first box and the third box are made up of just one type of shape versus the second and the fourth are made up of multiple shapes or shapes and colors, right? Okay, so that's an observable difference here. And then Riley went a little bit deeper and he said that he looked online and they said that if there's the same 2 elements, it is not a compound, right? If it's the same 2 elements, it is not a compound. All right, so like hydrogen gas, okay? Hydrogen gas is a perfect example of it being the same 2 elements, okay? So it is not a compound. All right, awesome. So then moving forward here for the sake of time and drawing skills. All right, if you would have typed in states of matter into Google and typed in the word particle, you would have come up with something that looked moderately like this. Okay, so a solid, all the particles are together, they're touching, they're neatly arranged. And obviously now we also know that we could have something where they're still touching, but maybe not as neatly organized together, right? So again, this would be our amorphous versus our crystalline. And my iPad's delayed, there we go. Amorphous versus crystalline, all right? But with our liquid, you should have showed them a little bit more spaced out. filling the entire container. Or not entire, it doesn't have to be entire, I'm sorry, but filling the walls of the container. So again, if I were to draw my liquid line, it would look something like that. Goes side to side, it fills up the sides of the container, takes the shape of the container. Then obviously with our gas, they're going to be incredibly far apart, still going to the edges of that gas bubble. All right. And we talked about this here. This, if it's solid, it has a fixed shape and volume. It's one set size, one set shape. Yes, over time, that shape and size might change. That is over time. Right? So in general, fixed shape, fixed volume. Okay? For liquids, it's obviously only a fixed volume, not fixed shape. Again, I could take my water, put it in a plastic water bottle. I could put it in a bathtub. I could put it in a sink. It's going to take on whatever shape of the container. So it does not have a fixed shape. But I can't miraculously make more water or change the amount of water that I physically have. However, with a gas, right, it definitely doesn't have a fixed shape and it does not have a fixed volume. Reason being for the fixed volume, because the gas is compressible. Okay, because our gas is compressible here. All right, I can push that gas together. And smush it down, right? So again, if I smushed it down, I'd have the same 5 particles, but they're just tighter. Oh, I'm sorry, you couldn't see that. Just tighter, compact. All right. I think the bell's gonna ring here shortly. But basically with this last one here, or the second to last one, why is it easier to walk through air than walk through water? Because if you're walking through air, it looks like this, versus when you're walking through water, those particles are tighter packed together. So you have to actually move through more particles. Okay? Now, hopefully you guys did this last one here super quickly. Sorry. Solids, liquids, gases. Okay? You're going to have the 4. So if I go from a solid to a liquid, I'm melting versus freezing. Okay? And I'm going from a liquid to a gas. I am evaporating. Gas to a liquid, I'm condensating. All right, those are the 4 major ones. All right. Other than that, boys, like I said, if you didn't turn something in, get that turned in because we're going to use it tomorrow. Okay? Goodbye, goodbye.
I got a quick question real quick.
Hit me. Yep.
For the project, I normally do my homework in the morning, so I knew it was due at 8 o'clock, but I turn it in before 8:30, which school starts. Is that all right, or will I get 10 points off?
That's fine. I'll change the due date time to 8:30 instead of 8 a.m. for all assignments moving forward.
Thank you.
Thank you. Goodbye.
All right, have a good one.
Bye.
You too.